Hey y'all, welcome to your next flipped classroom video. This is a lesson related rates. This is one of those guaranteed free response kind of questions. Is a related rates topic, but you can imagine the reason this is included in the derivatives application section is because of that word there. It's because of the word rate. We normally know that we've been using the phrase rate of change since somewhere in mid pre-calculus. That was a word that we coined instead of slope, but we also kind of added another word to it at the end of pre-calculus and all of this year. And we've based this whole course so far has been based off of the rate of change, the slope, also known as the derivative. So what we're doing here is we're actually going to be taking the idea of the derivative, and not just derivative, but implicit differentiation. Remember the dy dx thing? When you take derivatives of different variables, you have to include the dy dx. So related rates is actually the only type of related rates problem is a word problem. And so related rates is a word problem in which we're going to have to use the derivative. We're going to have to use dy dx or, whatever variable we're talking about here. So there's a step-by-step thing. I like to remember it using the word dreads. I'm not talking about everybody's favorite receiver. That's not the type of dreads I'm talking about, although, how about those Tigers? I am talking about this type of dreads. So the first thing you're going to do in related rates problems is you're going to draw the situation. Like I said, it's only word problems, so you're going to have to draw out the situation. Labeling these problems will earn you a point. Correct labeling will earn you a point on these related rates problems. So those of you that are anti-writing things down, related rates problems require you to draw and get the labeling correct. All right, after you draw, you're going to recognize some sort of shape, some sort of equation that you've known back from geometry or from pre-calculus. And so you're going to have to remember the equations that have to deal with whatever the picture turned out to be. Of course, because we're talking about related rates, rate of change, you're going to have to take the derivative. After you take the derivative, though, you're going to have lots of different variables. Remember, we're taking the implicit differentiations. You're going to have some plain variables. You're going to have some dy, dx kind of variables. You're going to have to determine what you know and fill in the stuff that you know. And after you fill in the stuff that you know, it's every mathematician's favorite step. It's just to solve for the answer. So what we're going to do is we're going to draw, remember the equations, evaluate the derivative, fill in the things that we know, and then solve out what we're missing. So here we go. At noon, which is going to be important here at the end, at noon, ship A is 100 kilometers west of ship B. So it looks like I have a situation where two ships are really east-west, but A is west of ship B. Ship A is sailing south at 35 kilometers per hour. What is that? 35 kilometers per hour. That's a rate of change. So watch this. I'm going to say dA dt. The derivative of A, the change of A over change of time is equal to 35. Did everybody get that? That the D means derivative and derivative means rate of change. So the rate of change of ship A is 35. Ship B is sailing north at 25 kilometers per hour. There's another rate, so I can say that the change in ship B, that the way that the ship B is changing is 25 kilometers per hour. How fast is the distance between the ships changing? So I don't want to know what the distance is, but how fast is that distance changing? So what I'm being asked about, and I'll call that S for between the ships. So the question is, how fast is that distance between the ships changing 4 hours later? Well, what is the rate of change, or what is the difference between the ships 4 hours later? I don't really know a shape that does like this, but I can kind of manipulate this. You see how this dotted line here kind of looks like a hypotenuse? I'm going to redraw. I'm going to redraw right here with a right triangle. So I'm going to still let my dotted line. Maybe for visual purposes, it'd be better if I do it like this. Get my dotted line be going this way. So I'm still going to bring that dotted line down here. The distance between the ships, remember, was 100 kilometers. So I got 100 kilometers here. The rate of change between the ships, the way that the ships are changing, so the dA and the dV, so the way that this is changing here, so I'm going to say the difference between A and B. Watch this. If it's 25 going north, 35 going south, I'm going to say that the difference between the ships is changing at kilometers per hour here. or the ships moving south and west, south and north is 60 kilometers per hour. Okay. The question is, what is this? What is the ds/dt? So I think I can figure out using Pythagorean theorem. I'm going to say this 100 kilometers squared plus, what am I calling that? AB. I combined A and B squared is equal to S squared, the distance between the ships squared. This is the equation we know. So part 1, draw. Part 2, remember the equation, Pythagorean theorem. Part E is to evaluate the derivative. So DRE, evaluate the derivative. Derivative of 100 is just 0. I'm taking the derivative here, so it'd be 2AB, and then I took the derivative there, so it'd be derivative of AB with respect to time. The derivative of S squared is 2S with derivative of S with respect to time. Okay, so going back to my steps, I've drawn the situation, I've remembered the Pythagorean theorem, I've evaluated the derivative. Now I need to determine what I know. Here's what I know. I do know that the distance between A, B, if we're talking about 4 hours later, how far has ship A gone 4 hours later? Well, 35 times 4 is 140 kilometers. 4 hours later, how far has ship B gone? And 4 hours later, that's 100 kilometers. So that means that the difference between, or the AB has altogether, they've traveled 240 kilometers. So watch this, 2, and then in the AB spot, how far have those ships traveled? 240. DAB, over, so the difference here, the difference between the ships, we determined that was 60 kilometers. See how I'm putting in the things that I know? Is equal to 2 S. I can figure out this S squared because I can do this. I can do 100 squared plus, and what did we decide AB was? AB was 240 squared is equal to S squared. Using a calculator, let's see. Let me pull up the calculator real quick. I'm going to pause and pull up my calculator. Okay, so remember, I'm looking for the things that I know. I'm determining the things that I know. And I know 100 kilometers is where they started. They started 100 kilometers apart. AB represents the ships traveling north and south. In terms of north and south distances apart, I've determined they're 240 kilometers apart because of ship A going 35 kilometers per hour and ship B going 25 kilometers per hour. So I'm going to figure out what that S squared is. So 100 squared plus 240 squared. 100 squared plus 240 squared. And I'm doing Pythagorean theorem here, so I want to know the square root of this. I don't know why I raised 1/2. Could just done the square root of that number. So 260. So that means that the hypotenuse of my little triangle here, the hypotenuse here. So 4 hours later, that hypotenuse is, what did I say? 260? Thank you. 260. So 260 kilometers. So S is equal to 260 kilometers. Filling in what I know here from my derivative. Why did I take derivative? It's because it's called related rates. It's wanting to know how fast the distance between the ships is changing, how the rate between the ships at 4 p.m. So the S was 260. And then look, the only variable I have left is the SCT, the change in the distance between the ships. And so then you would figure out, I'm going to let those 2's be done. So that's 240 times 60 divided by 260. So 240 times 60. And then to get ds dt by itself, I'm going to divide over by 260. Should be 50, yeah, 55.384. So ds dt, the answer to this question, since the question was how fast is the distance between the ships changing, the answer is 55.384, whatever that decimal was, kilometers per hour. It's related rates. It's taking a whole situation. You're going to be able to put, almost like a puzzle, you're going to be able to put all the pieces together except one piece, and that's the piece that you should be looking for. That's the part of the question that the question should be asking you. Let's read one more together. Let's see, I have one more, two more. Let's read Yeah, let's read through this one together, and then I'll draw the picture and get you started on this next one, and we'll finish it in class together. But however, this one. All right, so I'm going to go through all the steps. So the draw part first. So a baseball diamond is a square with sides of 90 feet. All right. A baseball diamond is a square, so that means all these sides are equal. Ooh. It's a square. And all these sides are 90. So 90, 90, 90 you get. A batter hits a ball. So from home plate, a batter hits the ball and runs towards first base with a speed of 20 feet per second squared. So that means that here, this change, I'm going to call the change in the run, in the runner, he is running at 20 feet per second. At what rate is his distance from second base decreasing? So I want to know if this is second base. I want to know this right here. So the difference, the distance between the runner and second base. At what rate is that decreasing when he is halfway to first? So halfway to first, let me draw a little side triangle here. All right, so here's my base path from first to second. What will be the length from first to second? Well, they told us that it was 90 the whole way around. If he's halfway to first base, that means that he's 45 feet away from first base. At this halfway point here, you could figure this out using, that's it, you got it again. We decided what we call that, S, between the runner and second base. You could use Pythagorean theorem here to figure out what this S is. So I'm just putting all the puzzle pieces together first. And here, I'm going to go ahead and write Pythagorean theorem. Remember, you need a couple different variables. So I'm going to say he's running, this is him running to first base. We decided that R, that base path to first, was R. Remember dr dt. And then this base path from first to second, that's not going to change. That one's just 90 squared. Okay, so 2s, I'm taking the derivative now, so the change in s, that's my question right there, was the ds dt. So I'm actually going to be looking to solve for this part here. 2r dr dt, because I'm taking the derivative of r plus, that would be just 0, so I'm not even going to write that anymore. So the steps were to draw the picture, so there's my pictures, drawn both pictures. To remember the equations, I decided to remember Pythagorean theorem. To evaluate the derivative, and then to determine the stuff that you know. So let's determine the stuff that I know. So 2s, I can determine s because of this Pythagorean here, because of the s squared is equal to 45 squared plus 90 squared. So let's figure that out real quick. 45 squared plus 90 squared, and then take the square root of that. So the s, the distance from him to first to second base, 100, I'm going to write that down so I don't forget it, 100.62306. I'm going to go all the way out to that decimal place there. So I solved for s. When he's halfway to first, he is 100.62306 feet from second. That's how far away he is from second base when he's halfway to first base. So in that s spot there, I'm going to put 100.623. You want to use as many decimal places as you can. When I go back and do mine, I'll probably use all the decimal places. ds dt, how fast is this change? This is changing to second base. That's what I don't know, so I need to leave that as a variable. To r, we decided that if he's halfway to first base, then he has run 45 feet, and he is running at a rate. So the dr dt, I'm going to put in 20 in that place. Dr dt. Then it's a matter of just solving for ds dt. How fast is he running when he is halfway to first? What is the distance? How is that distance changing between runner and second base? So that's what you would solve for here. I'm going to help you set up one more. You probably want to go ahead and have it jotted down so you can finish it in class with somebody if you're paired with somebody, or if you just have to finish by yourself. Let's draw this third one together. And that's some notes for that I want to show you next class. Okay. Let's draw the picture. So a conical water tower has a height of 10 feet. So let's think, if it's a conical water tower, I'm going to assume that the point is coming down, because you're going to want the water to all funnel out to the bottom like this. Conical water tower has a height of 10 feet, So that means this height here, a height of 10 feet, so h is 10 feet. A radius of 5 feet, r equals 5. Water is pumped into the tank. So the volume, that means the water inside this tank, the volume is pumped into the tank at 9 feet. Should be feet squared, right? If it's volume going into this, so it's, no. Volume's totally cubed. Duh, Miss Jenkins. Feet cubed per minute. How fast is the water level rising? Check that. How fast is the water level rising? So what's it want to know? It's want to know the water level. Kind of sounds like height. The question is dH dt. When the water level is already, so when height is 6. This is the scenario that I'm being asked about. I'm being asked about how fast is the water level rising, how fast is the height changing when height is 6. Okay, so I'm talking about the volume. It just told me that the volume, the 9 feet cubed per minute. So I know that the volume of a cone is 1/3 pi r squared h. Okay, so I have my picture. I remember my equation. Remember the E part is to evaluate. So the derivative of V is actually dV dt. 1/3 pi, check this out, r squared times h. That's the product rule, so let's do the product rule. Leave the first, derivative of the second, dH dt, plus leave the second, derivative of the first, so that's 2r dr dt. Now think about it. You see that you're being asked about dH dt. You were given dV dt. Where in this problem would you find anything about dr dt? Where does it say anything about how fast the radius is changing? And so at this point, we have a little gut check, and we realize, crap, we don't know anything about radius. So I'm going to back this bus up. We realize we don't know anything about radius. So I'm going to come back to just the original volume equation. And instead of writing anything about radius, I'm going to try to manipulate to where I can fill in for radius using what I know about height. Look up here at your original picture. What do you know about the relationship between radius and height? You can tell that the relationship between radius and height should be equivalent to 5 and 10. All right, so the fact that I know nothing about radius means that I'm going to want to put as much information about height, because that's the only thing I know about, or that's the only thing I'm being asked about, being told anything about. I want to put as much information in here about height as possible. So I'm just going to use a little cross multiplication, a little old school cross multiplication. And I want to solve this for r. So r is equal to 5h over 10, so 1/2 h. So check this out. If I put 1/2 h in this r spot, in my new equation, that would be 1/2 squared, so it'd be 1/12, because 3 times 4, pi h cubed. Check that out. Now my volume equation is totally in nothing but height, which is good because that's what I was being told about and asked about, is height. So I'm going to try that volume. I'm going to take that derivative again. dV dt equals 1/12 pi times 3h squared. I took the derivative of h, so dH dt. Let me clean that up a bit. To 1/4 pi h squared dH dt. Remember the steps. Determine what you know. We know the dV dt because it says that the water is being pumped in at 9. Determine what you know. 1/4 pi h squared. What did it tell us about h? H squared dH dt. And that's what you're solving for, is the dH dt there. Okay, so below this video, there's another video. A classic related rates problem is a ladder problem. There's a man that does an excellent job solving the ladder problem. That's attached. A link to that video is attached in the bottom here. So if you need another video related rates, and going back and watching this is maybe not going to be as super helpful as you think it might be. You're more than welcome to go and look for this guy's video. He does an excellent job of describing related rates. We're going to be practicing a ton more of these, so if you're thinking, I think I can get it if I get more examples, in class, the reason you're watching the video outside of class, so that in class you can spend as much time as possible getting a grasp on how to solve these for yourself. Again, watch this video, email me questions, and I look forward to solving some of these problems, because these problems can get kind of fun, and that's kind of a nerdy thing to say, but these problems can get kind of fun. I encourage you to get a grasp on this. If you haven't, as this video has left you like, okay, I think I see what's happening, but I'm not totally sure, I encourage you to maybe ask for another video, or get some specific questions that you have in class. But this is related rates, rate of change, it's all about the derivative, and we're answering specific word problems based off of the derivative application. All right, I'll see y'all in class. See ya.